Hey everyone, we're going to start new material now on reactions at the alpha carbon, and I'll talk about what that is. We're going to start though with this review. And this is from probably second quarter organic chemistry. You probably saw this when you had a triple bond and you were adding, let's say, acid catalyzed water. You're doing acid catalyzed hydration. And you would add an OH group to the more substituted carbon. Let's just pick one. And when you added that OH group, and you have other groups on here, then you ended up with a new functional group with an alcohol and an alkene, which is an enol. Okay, you ended up with an enol. And that enol, you probably remember, had to tautomerize to a ketone, okay, or keto form. All right, so in an enol form and a keto form, and you probably learned a little bit about the mechanism for that. So we're going to review that. How does that mechanism work? So it actually helps if you have acid or base in solution to make this reaction go faster. And so what I want to leave you with right now is maybe practice where you take the keto form. Let's say we just take this molecule acetone and we try to get the enol form from it using acid catalyst in water. Okay, you should be able to go this way, and you should also be able to go this way with the mechanism. Let me give you a hint. You need to think about these hydrogens over here or on the other side right here. Okay, so think about these and how you might interact all this to make the enol. And then as a second problem, we'll see if you can do the base catalyzed one as well. So now take the same thing, but instead of acid, we now have a basic environment, and see if you can do that as well. And by the way, this is an enol, so I should have put that pi bond there. Okay, so ketone to the enol, keto form over here to the enol as well. See if you can figure out a mechanism, electron pushing mechanism, to do these two reactions. All right, and for now, let's just go forward. Okay, so from here to here and from here to here. All right, starting with the ketone over here, if it's acid catalyzed, you probably remember doing that kind of thing just even a few weeks ago, right? Or recently. And once we have this, then notice that this pi bond breaks and we have two lone pairs here. So I'm going to push the electrons up like this. And what I probably need to do then is have something to form the pi bond for my ene of the enol right here. So that's what I'm going to do with my water. Is I'm going to grab one of these hydrogens and do that. Okay, so that's how the mechanism for the keto to the enol goes for acid catalyzed reactions there. And then over here for the base catalyzed one, I need a way of eventually protonating this O, probably from water, but I need to form the ene or the pi bond over here. So for this one, I think I will take this hydrogen with my base and do this, and then that's going to give me this intermediate, and then I can protonate that with water. So be able to know how that mechanism works, because we're going to use these concepts a lot in this chapter. Also, for you, I'm not going to do it here, but go ahead and practice going backwards. So how do I take the enol, and how could I use acid and water to make the keto form? Because there's an equilibrium. This is reversible. It's an equilibrium between these two. Okay, and same here. How do I use this base and go backwards to the keto form? All right, so that's your first mechanism to learn. So on a separate sheet of paper, draw these out and practice doing these again, forward and in reverse. Now, since both of these are in solution, it's good to know which is favored. Now, usually the keto form is favored thermodynamically. The CO double bond is more stable than the CC double bond. That's because the mass of oxygen is greater than the mass of carbon. So normally the keto form is the favored form. However, that's not always true. sometimes the enol form could be more favored, and there's just a few exceptions you should be aware of. So one of the exceptions is if you have a dicarbonyl compound. Let's say one carbonyl is alpha beta to the other. Okay, so beta to the other one. Okay, so if you see that pattern, what happens is often we see that there's evidence for this right here. This one over here is in its enol form. This one remains in its keto form. And the reason why this one's favored over this one, maybe you can see what that is. There's two possible explanations. One is you might see sort of some conjugation here. So this is what we call an enone, where we have resonance stabilization there. So you might picture something like that. Another thing that's helpful with this one is this intramolecular hydrogen bond. So that helps to stabilize this molecule in this form. So the enol's favored for these two reasons. Over here, this one's also showing that the enol form versus the keto form. Here's the keto and here's the enol. If we take a look at this, why is that so much more stable in the enol form? I think you guys can see there's aromaticity here. When it's in the enol form, we have the pi bond and then we have aromaticity. Here we don't have aromaticity because this part is not conjugated with this system here. So it favors enol in that case. So you always have to sort of think about the previous concepts we've learned before. Now moving on here, we've been learning a bunch of reactions where you have a nucleophile or base that attacks the carbon. So in that context, it's a nucleophile. So nucleophilic acyl addition, and then if this group is a leaving group, then you can have addition elimination, or also called substitution. Now there's many possibilities for then a nucleophile or a base coming in. If we have a base, bases, rather than attacking the carbonyl, they'll grab a hydrogen. So that's why base is appropriate here. So if a base could potentially grab 3 different kinds of hydrogen on this molecule, let's say the purple one, the blue ones here, or red ones here. Okay, so 3 different kinds of hydrogens on this molecule. Go ahead and let's draw out all the possible conjugate bases of these molecules when the base deprotonates each kind of hydrogen. So let's do one together, and you guys practice doing the rest. So for this first one, let's say if the base grabbed this hydrogen, what would we end up with? And one thing before we do these is I want to ask you, which of these hydrogens looks the most acidic to you? Do you think purple, blue, or red? Which one of these looks like it's more likely the base will take that one? So go ahead and write down on your paper, I think this one will, or I think this one will, or I think this one will. And write down, pause it, think about it, write down which one you predict and why you think that hydrogen is more acidic. Okay, go ahead and do that now. And then go ahead and write the conjugate base, so the result of these arrows, and then we'll go through those in a minute. All right, I hope you had a chance to make your prediction. We're going to go over it now. If I deprotonate each of these hydrogens, these are the resultant conjugate bases for these ketones or aldehydes in this case. And you also have your protonated base as another product. Okay, looking at these 3, we know that the more stable this is, the more likely the reaction is to go forward. So I want to evaluate the stability of each of these conjugate bases. If you look at this one's not very stable at all. Actually, I think a lot of students, when they see this aldehyde, they think, oh, that hydrogen looks special. I bet the base will want to grab it. Actually, it's the opposite. The base does not want to grab that hydrogen. And if you think about it, remember back to when we said this is a good electrophilic part right here, the carbonyl carbon. Well, if that's a good electrophile, that's partial positive, then we don't want to have a negative charge on that carbon. It's very unstable to have positive next to negative, or even on the same carbon. It doesn't make sense. So this is not going to be very stable for that reason. All right, for this next one, you can see this is going to be a pretty strong base, not very stable at all, because it's a lone pair and it's on a carbon and it's very nucleophilic. In general, carbon with a lone pair and negative charge is very nucleophilic. Well, this one over here is also carbon with a negative charge, but do you see why it's not as nucleophilic as this one? I hope you can see that it's in conjugation with this carbonyl group right here. So that means it's going to be resonance stabilized. That means this conjugate base is the most stable of all three, which means this is the most acidic hydrogen. And these are what we call the alpha hydrogens. So you take the carbonyl, and alpha to that is the first neighbor, and beta to that is the second neighbor. And then it goes gamma, delta, epsilon, and so forth. Okay, so alpha hydrogens are going to be the most acidic ones. And the pKa for these alpha hydrogens are generally 19 to 20. Okay, so I'll just remember 20 because it's easier. So that might help you compare them to other functional groups we've learned, like alcohols and water are generally 15 or 16 pKa, so they're stronger acids. But alkynes are about 25, terminal alkynes are about 25, so they're going to be less acidic than these. So that helps you sort of know if I had a base in solution in multiple functional groups, what are their relative acidities. So the one that's stabilized by resonance, this one's what we call the enolate ion. And the enolate ion is something we're going to see a lot of in this chapter. Enolate, because it looks like an enol, but it's negatively charged anion. Okay? So this enolate has a resonance structure that we should probably draw because we want to be able to look at this in many different ways. So sometimes you see the enolate ion with the negative charge on the O, and sometimes you see the enolate ion with a negative charge on the carbon, the alpha carbon. It's more likely that we're going to use the enolate in this form over here, and that's because this carbon here is our nucleophile for many of the reactions we're going to learn. All right, so here we want to practice figuring out which hydrogens are the most acidic, and we can also practice drawing our enolate ion. So let's do that. So which of these hydrogens are the most acidic, alpha, beta, or gamma? Well, we just said it's the alpha hydrogens, unless you were dozing off, which I understand. Some people tell me my voice is very relaxing. It's a nice way of saying you're boring. But anyways, yes, it's the alpha hydrogens. So just pick one of those. In this case, this molecule is pretty symmetric. So you can just pick any one of these to make your enolate ion. So one thing you could do is you could picture a base coming in and grabbing one of these and putting your negative charge here. And then the resonance structure for that is to have the negative charge on the oxygen. Okay, so there's the other resonance structure there. All right, so as we mentioned, the enolate ion can be in two resonance forms, either the O minus or the carbon negative charge carbon. So you could have an electrophile attack or have the oxygen attack, or you could have the carbon attack an electrophile. Normally, we think of the oxygen as being a hard nucleophile, and its orbitals are usually compatible with hard electrophiles like hydrogen ion. Those tend to get protonated really well, and then you make your enol. But the carbon anion here is usually what we call a soft nucleophile. It prefers other carbons and groups that are more electrophilic with softer orbitals. So it prefers soft electrophiles. You'll start to get a sense for what's hard and soft. So with respect to nucleophiles and electrophiles, because there's a compatibility issue that will help us predict the reaction better. So for now, just think of the oxygen as getting protonated more easily, but in terms of nucleophile, it's the carbon that acts as a nucleophile in most of our reactions. All right here is just some practice from Klein on how to draw the enolate and practice the resonance structures. So identifying which carbon is the most acidic one here, there's 4 possible ones. Because of the symmetry here, you could pick any of these 4. So I'll just draw it like this. And then you can also draw the resonance structure like that. All right, my pen is acting up again, but it looks something like that, okay? So go ahead and practice, and also you can practice your electron pushing as well. Like you can do this and do that. You can also come down and over here. It's good to practice your electron pushing as well. So go ahead and finish these up and you can check your answers in a minute. Okay, here we are. So I just drew the, I identified the alpha hydrogen. In many cases, there's only one. And later you'll learn how when there's different ones, which one is more likely to get deprotonated with which base. So, but for now, just identify the one alpha hydrogen type that is going to be deprotonated. Next, we're going to talk about different base strengths. So there's different things you could use as bases to deprotonate those alpha hydrogens. So let's give you a chance to think about something. We have two different bases here. We have ethoxide and we have LDA, lithium diisopropylamide. They are not the same base strength. And so you might need to figure out which is a stronger base. And there's some pKa values for their conjugate acids over here as a clue, okay? So I want you to figure out which of these reactions, top reaction or bottom reaction, which one do you think will make more of the enolate in solution? So go ahead and pause it and think about that and really try to figure out a line of reasoning. All right, so we can see from the conjugate acids that this is a stronger conjugate acid than this one. So therefore, this as a base will be stronger base than that one. Okay, so this LDA is a stronger base. So that means that it's going to be able to push the reaction forward more than the other one. That for us means that if we can use stronger bases like LDA, then we're going to get more enolate, which is great if we want that. But it also could mean that ethoxide won't give us as much enolate at the beginning. But once we use up that enolate, then the reaction can shift forward via Le Chatelier. Remember, removing a product means that the reaction will go forward in response to that. So often, even though we might prefer LDA, it might be easier just to do the reactions with ethanol in base to give us ethoxide. So you'll often see both bases being used in this chapter, and that's fine. Another thing to consider here is notice the ethanol and this alpha hydrogen have similar pKa's. So this reaction isn't terribly reactant or product favored. It's maybe a little bit more reactant favored, actually. But as I said, as this enolate reacts, it will drive the reaction forward. Explain why hydroxide or ethoxide is suitable for this compound, however. And let me give you a hint. This hydrogen is actually much more acidic than the ones up here. These, if you want a reaction to go forward, you could use a stronger base like here, or you could use a weaker base but use a stronger acid, and that's what this is here. These hydrogens are more acidic than just your regular alpha hydrogens. I want you to ask you guys, why do you think that might be, that this molecule has more acidic alpha hydrogens? Maybe let's compare this molecule structure to this one. What do you see that's different? Well, I see that there's a difference in the number of carbonyl groups. So it turns out that when you deprotonate this, let's draw the enolate for that. When you deprotonate this, your enolate is actually can have resonance structures with either carbonyl group. So either you can have this or you could have this, right? Well, that means that you've got more resonance delocalization overall. So that means this molecule is going to be more stable than these guys over here. So that means that this reaction's going to be favored in a basic solution. So normally we see the pKa of these as being around 15 or so. All right, so looking at all these different carbonyl containing compounds, let's try to figure out an appropriate base. And so what they really want us to do is practice using LDA for a single carbonyl, and then for dicarbonyl like this, you can use ethoxide. That would favor enolate formation. And ethoxide, you might as well use ethoxide. It's easier to use than LDA. LDA is sort of complicated to work with. It's usually very cold. It's very reactive as well. So you don't really want to have to use it unless you really want more enolate. Okay, so we only use LDA when we really have to. All right, so for the first one, I see a dicarbonyl here. So I know that these hydrogens are more acidic than just having one carbonyl. So these alpha hydrogens are fine to be removed with, just sodium ethoxide or hydroxide or methoxide. Any of these kinds of bases, they're all very similar to each other in their strength. Okay, and I'm writing their anion, but of course you could have a sodium counterion or potassium counterion. Just be used to KOH, NaOH, KOMe, NaOET. Any of those are fine. So there's the first one. I can use any of these bases, and even though they're the weaker base than LDA, that's sufficient because these are more acidic. So, okay. So now you guys try these and we'll come back and check our answers. Okay, so for these, I found that this is not stabilized. These are not beta to each other. So that's going to be treated like a regular single carbonyl here, and here as a single carbonyl there. So these pKa's are not going to be as low as these. So in that case, let's use a stronger LDA, and we'll just get one of those enolates that are possible. And then over here, the only alpha hydrogen is here. So it's just one carbonyl, so we'll use LDA as well. Now the one consideration for this one is that you might use sodium ethoxide anyway, just because this is very bulky here. So you've got a branched alpha hydrogen. So LDA, if you look at the structure again, it's lithium diisopropylamide. So it's pretty branched, so it's not a very good nucleophile. And so here as well, it might be hard for this branch to come into this branched site as well. So for that reason, you might sacrifice base strength for, using a smaller base. Might be a kinetic thing going on there. For 22.7, there are many alpha hydrogens on here. Let's find them all. Okay, so we've got these alpha hydrogens here. We've got alpha hydrogens, where else? Here. And we also have alpha hydrogens here. Okay, so my question for you is think about which of these hydrogens might be the most acidic and why. And would LDA be required, or could sodium ethoxide be adequate? And then draw the resulting enolate. Go ahead and give that a try. All right, for this one, you really need to understand resonance. So if I deprotonate here, I'll end up with a resonance structure that spans this side of the molecule here. So that's nice. But if I keep going over here, if I have the enolate, it will also go into the carbonyl. But hopefully you saw that it will also resonate into this side of the molecule as well, because it's conjugated throughout this whole system. With these guys over here, it can only go this way. So these on the end can only resonate into the carbonyl group, whereas the ones in the middle here can go into the carbonyl and also go across the molecule, because this is all a conjugated system. So it's these red ones I have that would be more acidic. And because of that conjugation, it's likely that a weaker base like sodium ethoxide would be adequate for this. So let's draw the enolate. So the enolate that I would expect you to draw is this one. And then you can show how there's resonance all throughout here. And sodium ethoxide would be adequate.